Let me first introduce assistants today. Ruth Shabai is going to make a video of this, which we'll put on the web for other people to see and for you to see. You've got also the slides that you can take notes on during the talk. Ruth's great merit in this is that in 1997 she realized she couldn't really teach an authentic intro physics course if it didn't include serious computation. And so here we are. Titus has been the head of the Department of Physics at High Point University. He's now finally shucked that duty, and he will be a co-author in the Matter Interactions curriculum that Ruth and Aaron and I are involved with, and which uses VPython. Steve Spickelmeyer was a major contributor to the last classic VPython, VPython 6. He's at the University of Indianapolis. He's currently completely swamped by helping them get their engineering college started. Both Aaron and Steve have very, very extensive programming experiences. Aaron was the co-creator of WebAssign, one of the widely used computer homework systems. Steve wrote a book on a package for an environment for using Python in. So they're very knowledgeable about this and have contributed to the developments of VPython. So that's who we are. Before starting the formal presentation, here's what we're going to do. I'm going to make a presentation about the architecture of the GlowScript library that is at the heart of GlowScript VPython, but also VPython 7, where you've got an installed Python, but it talks to this same GlowScript library. Then I've invented some tasks for you to modify the GlowScript library right here on your desk and try running a revised version of it. And so I don't know exactly how long the first part will take, but the rest of the time will be you guys doing things. Now, who managed to actually get the software onto their machine? Okay, so most of you did. And if you didn't, you're just going to look on with somebody who did and watch them, and you can work together on it. And you can also work together even if you have both machines working. So that's what we're going to do. Now, at the very beginning, I guess I should ask, are there people in the room who have never actually used VPython in one form or another? Okay, it's 2 of you. 4. How many of you have never been at glowscript.org and written and run a VPython program at that website? 1, 2, 3. Okay. So I'm going to, at the beginning of this presentation, I'm going to make it very, very quick in showing of what GlowScript is and what VPython is, just for the people who are going to see this video on the internet and might not know, but they were curious about the rest of it. So with that preamble, are there any questions before we start? Like, why are we here? Or what is the meaning of life? Or, okay, all right.
Is it going to be on the test?
Yes, this will be on the test. And actually, I have to warn you that the questions aren't necessarily exactly the same ones that were treated in class. I hope you understand that. Is that okay? All right.
Study guide.
There'll be a practice test available. Okay. So, the architecture of GlowScript VPython. VPython goes back to the year 2000. I'll say a few more words about that. The GlowScript version of VPython goes back to about 2015. And there's a little bit of history before that as well. And as I said, for the benefit of people who are viewing this video on YouTube and have never actually seen VPython and not seen GlowScript VPython, let me just show a little example to give you the sense of what that thing is. At glowscript.org, now I'm actually running locally, but at glowscript.org, if you sign in with a Google account, then you can write programs by, I'll say, create a new program, and I'll call it test. And it already provides for me a first line that says we're going to be using the 2.9 version, and I guess I should make it bigger, right? Is that okay? And let me write a 3D program. This is a 5-character program, and I'm going to run this program, and when I run it, what it generates is, and I should expand this window a bit so you see the whole thing. What I get is a 3D cube, and I can rotate the camera to look at it. I can pan back and forth. I can zoom in and out. And this in itself is pretty extraordinary. Most programming environments that do 3D would require pages and pages of the most arcane code imaginable. So this is kind of unheard of, and it's what makes it possible for ordinary mortals to write programs that generate not only 3D images, but even 3D animations. And to give an example of that, let me show you a binary star program. Here's a binary star program, and I'll make it just a little bit smaller so you can see it also shows instructions on how to use the camera. And again, and you can zoom, and you can pan, and it's got these mouse controls and all this stuff. And if you look at the program, it's remarkably short. The first few lines are just that text that you saw displayed on the screen. But then, this is a physics program. We define Newton's gravitational constant. We create a sphere object which has a position that's a 3D vector, x, y, and z, x to the right, y up, z out, right-handed. We give it a radius. We give it a color. We say, I want you to leave a trail as it moves. I want to leave a trail behind it of the points kind instead of the curve kind, so individual points, not connected. We'll do them every 10 moves. We'll add another piece to the trail, and we'll retain just the last 50 so that you get sort of like a comet-like trail. And also and we're going to give a name to it, giant, and this giant will have a mass, so we can add our own kinds of attributes to this instance of the sphere class called giant, and size of the sun in meters. And we're also going to give it a momentum, which is a vector times its mass. And then we create another sphere. This time the trail is by default a curve, and we call it dwarf, and it has a smaller mass, and it has the negative. It starts out having a momentum opposite of the other one, so the total momentum is 0, so that this binary star doesn't move through space. And then we choose a time interval of 10 to the 5th seconds, and it will write an infinite loop which says, while true, at a rate of 200 iterations per second, so this says clamp the iteration so it doesn't go too fast for you to see anything. So no more than 200 iterations of this while loop per second, no matter how fast your computer happens to be. And here's a vector statement that says, take the position attribute of the dwarf sphere and subtract the position of the giant sphere, and that's a relative vector pointing from one to the other. And the next statement is we calculate the gravitational force. It's big G times the giant's mass times the dwarf's mass times r hat, unit vector, divided by the magnitude squared of that vector. So notice these are all vector statements. And now the force times that time interval is the impulse, which in the next time interval adds to the current momentum to give the new momentum of the giant. And for the dwarf, it's just with a minus sign because the reciprocity of the gravitational force. Next, we take, as representative of the average velocity, we take the new momentum divided by its mass, multiplied by the dt, is the three-dimensional displacement vector, which added to the current position of the giant gives us the new position, and similarly for the dwarf. This is called Euler-Kromer integration. Calculate force, calculate the change in momentum, use the new momentum as representative of the average momentum, and oddly enough, that works best. You know, one first order Euler integration, this particular sequence of operations, it preserves phase space, it does a good job of conserving energy, and being first order, the computers are fast enough that even just this first order stuff, they run fast enough. So the thing we teach our own students about numerical analysis is cut the time step until the behavior doesn't change. And that's adequate. So as you can see here, there's a tremendous number of well thought out, well designed defaults. It says if you want to just make a box, well, we'll set up things to show you a box. We'll set up lighting, etc. And there's also a lot of elements of this programming environment called VPython, syntax of VPython, which are aimed at the task of making navigable real-time 3D animations. And by the way, when you set things up, we're going to create not only some lighting for you, default lighting, we'll also by default put the camera in a position where you can see the scene, and the scene kind of fills the camera view, and so there are elements of the thing that are supportive. Again, writing this program in other 3D environments is off-scale difficult. It's just plain off-scale difficult. There do, of course, exist many environments for creating 3D scenes, static scenes, and they may be just purely manipulative. You might not even have to write code, but to write animations and so on. So that's what VPython is about. What is GlowScript VPython about? At glowscript.org, as you saw, you log in, you write your program like this, you run it here, and you can also send somebody that link, and they can click on the link, and they're running the program. They didn't have to install any software. Prior to 2015, students writing VPython programs had to install Python. They had to install VPython. If they're on Mac, they had to install an update to something called TCL. This was very scary. It was very daunting. We had no idea how big a barrier this was to students until in the fall of 2015, Georgia Tech switched from using that Python. Student enthusiasm for acceptance of VPython went way up. And for them, these are techie students. They're majoring in STEM curricula. They've never written a program before. They've never installed software. And you know from getting this stuff to run for this workshop how difficult it can be to install software. They didn't know about folders and files and file extensions. What they had to do to get VPython running was sending them a very clear signal. This is a very techie course and you're going to fail. And it was very, very threatening. Now they just go to glowscript.org and they're writing programs and running them. And the code is saved automatically in the cloud for them. They don't even have to save the files. It's just auto-saved every few seconds. So it was a huge change. And so for students who have not had prior programming experience, GlowScript VPython is a big win. We do also offer the same syntax to be used with installed Python, and we sometimes refer to that as VPython 7. But you install Python, you install VPython, which has the same syntax. This program runs there just as well as it runs here. Actually runs faster than GlowScript version than with installed Python because this code gets converted to fast JavaScript instead of being interpreted Python, but that's a detail. So that's what this is about. And when students have used VPython at an introductory level, they're well prepared to go on to using Jupyter Notebooks or Jupyter Lab or more professional tools but still be able to use the same syntax. Are there any questions on this aspect of things before we go forward? Okay. Then back to here. Architecture. Brief history. The year 2000, David Scherer, a very talented student at Carnegie Mellon, which is where we were teaching at the time, proposed and created a 3D programming environment for our use called VPython. And there only a few people contributed to that code base from that time on, and that included Steve. David Scherer came back on 2 occasions and made some important contributions. Jonathan Brandmeier was an undergraduate at NC State where we were teaching it for a time. In 2011, I learned about a new thing in browsers called WebGL. Now, VPython had been using OpenGL, which is a widely used 3D graphics library, very low-level library, and VPython made it possible to do 3D animations without having to cope directly with OpenGL. By 2011, we learned that there was built into the modern browser a little sister of OpenGL called WebGL. And it has all this, basically the same properties, but it was a stripped down version so that things could run even in a 2011 phone. That looked like an opportunity, and David Scherer and I worked together. In 2 months, we put together GlowScript.org with its capabilities. He did much of the architecture, but I was his assistant. And since that time, I've been it for tag. And that's why we're having this discussion here, because we need more people who are being it for tag. In 2014, I learned from a programmer in France of Italian ancestry with the remarkable name of Salvatore di Dio, which literally would mean Savior of God, that there was a library called RapidScript, which could take Python code and convert it to JavaScript code will run in browsers. Python does not yet run in browsers. There's work being done to do that, but it's not there yet. And so I was able then to bring in RapidScript and convert Python code into JavaScript code and run it in the browser using the WebGL 3D library that was built into the browser. So that was a big deal. And as I said, by 2015, Georgia Tech was the first major place to have their students using it, and it was a big success. At about the same time, a programmer named John Cody had an interesting thought. Having seen the GlowScript library, he made a Python implementation of the VPython code that talked to the GlowScript library to make the 3D displays. and the next year, well, in 2016, Ruth and I worked together to harmonize the VPython syntax he was using, which was the older variety, with the GlowScript VPython syntax, which means that you can move programs one environment to another and they will still work. And we decided at that point we would stop work on the classic VPython. It was not sustainable for various reasons, and you can read about that at vpython.org. 2017, Matt Craig, who was to be here today, but he is at Moorhead campus of the University of Minnesota, in Moorhead, Minnesota, and it's so cold at snow and ice and whatever, planes weren't flying yesterday. So he won't arrive until this evening. But he's done great work in building installers for installing VPython with installed Python. And it's not easy. It's difficult work, and he's done a great job. So that's the brief overview. Here's the VPython you'll encounter at glowscript.org, and it's in the software that many of you succeeded in installing. There is a server code. There's server code that's a that's one file written in Python that serves stuff to the web page. And there is also in the cloud a data store where your files are held. Then over in the browser, there is the RapidScript library that converts your Python code to GlowScript. That JavaScript code is passed to that JavaScript code calls upon this library, which tells WebGL the arcane thing you have to tell WebGL, which then ends up putting the 3D on your display. And this same architecture is used at Trinket.io. Trinket.io has exactly this architecture. If you go to Trinket.io and you choose Python, one of the choices is GlowScript VPython, and another choice is blocks version due to utter close. Now, let's see if this starts to answer your question. This is what VPython looks like when used with installed Python. On your machine, you've got Python installed. You import the VPython module and possibly other modules, NumPy, whatever. There is an HTTP server which sticks stuff into a browser, sends stuff to a browser, including this a JavaScript program that receives that data, passes it to the GlowScript library, which talks to WebGL, which makes a display. There is also a WebSocket. This sort of gets things going, and stuff flows back the other way as well. But for speed, there's also a WebSocket server, and this is a kind of a server connection which is fast two-way. HTTP servers are relatively slow. You make requests to have stuff sent to you, or you send something to it, and then after that interaction, it's my understanding that basically that communication link is broken. The WebSocket server stays active and gives you high-speed stuff going back and forth. And so what's going back and forth, going this way all the time, is things like, make me a box, make me a sphere, change this sphere, color that box differently. And what's coming back this way is, here's where the mouse is now. Here's which object the mouse has touched. All that kind of communication going that way. Does that address your question? So necessarily, modern VPython cannot be used without this library running in a browser page. Now, Aaron just very recently did something which is about to be released any day now, because it was tried last night. I actually didn't get it all to work, as you maybe saw, where instead of it going to a browser, it goes to a Qt window. Yeah. But it's still the case that the architecture is this. Okay. Then there's one other subset of using VPython with installed Python, and that's running in Jupyter Notebook. It looks the architecture is very similar. The only difference is that in this case, it is the Jupyter Notebook machinery that's taking care of the traffic going both ways, instead of us taking care of it. And similarly, Jupyter Lab. So there are kind of these three different kinds of using it with installed Python. We do it for you. Jupyter does it with a notebook, or Jupyter does it with Lab. So I see these as kind of the three distinctive things. But then add in Trinket.io, and you can see there's kind of almost 4 flavors altogether. Other questions on this basic architecture? What we're going to be focusing on today is that piece there. That piece. And just to remind you, let's go back a page. This is where that fits in here. Now, there's more detail than shown on this graph, which is why we'll look at more of the details. And we'll start with how your Python program gets compiled to Java. the first thing that happens. You hit your program at glowscript.org, you say run. At that point, this RapidScript gets kicked in, and some other stuff that we'll see. RapidScript is a major piece of it, but there's some other stuff as well. This is what Python code looks like that converts into this JavaScript code here. And I want to talk through this in some detail to give you a sense of what happens here, because it's crucial. And it's subject to change. If somebody comes along with a better transpiler than RapidScript, fine. At the moment, there are half a dozen well-known, better known than RapidScript actually, Python to JavaScript translators. And all of them are much slower than RapidScript. The philosophy of RapidScript was go fast, make mistakes, go fast, do wrong. It does quite a good job of going from Python to JavaScript. There are edge cases that it doesn't do exactly the way Python would do it. For example, in Python, if you divide by 0, you get an error. In JavaScript, if you divide by 0, you get a special number called INF, infinity. RapidScript doesn't attempt to check every division to see whether there's a 0 or not. So your program would run differently in real Python than in RapidScript Python because it doesn't compromise performance for making it bit perfect to real Python. I do think, and I know that there's real experiments going on now, it's only a matter of time before Python runs in browsers. It has to, because getting to the browser has been a big deal for us, because previously, prior to using WebGL, it was extremely difficult to support VPython across multiple platforms. It was a bear, Steve remembers. And the browser's almost all alike in terms of their specifications and how you address them and how you get stuff from them. There are differences, but by and large, the browser has dealt with the cross-platform nightmare and saved our lives, basically. So this is a big deal. It can only get better as things better RapidScript or things better than RapidScript. RapidScript has also been good for us because the guy who supports it is incredibly rapid in fixing mistakes and errors. Typically with form, I report something and the first reaction is likely to be no, and then a half hour later it's fixed. So that's been great. Now, let's look at the details. So there's that first line, GlowScript 2.9 VPython. The 2.9 is a version number. It goes all the way back to around 2.2 or 2.3 or something. You can run old GlowScript VPython programs by saying 2.3 and they will still run because we've saved the libraries from that time. So we've been able to modify, improve, add, correct with new version numbers, knowing that your 2.7 program will still run. And that's because it's centralized. We have all the stuff. It's not out there with your Python that I can't actually change for you. So that's what that version number is about. A equals 5 times 3. That converts into something rather odd. First you'll see 3 in quotes. Now it's an off by 1 thing that gets fixed when reporting an error, but I insert quote 3 quote semicolon. That's a valid JavaScript statement even though it doesn't produce any result. It will survive going through the RapidScript and other transformations that have to be done and end up here so that at execution time, when you do something wrong in that statement, I can give you an error message that say, at line 2, this is what's wrong. So that's what these 3, 4, 5, 7, 8, and so on, that's what those things are. Those are inserted by me. and they survive RapidScript. This statement here looks very odd. A equals 5, left bracket, quote, asterisk, quote, right bracket, left parens, 3, right. What? What's that got to do with 5 times 3? So when in 2011, David Scherer was building GlowScript.org, there were 2 problems that he and I had to face, and he found solutions for both of them. One of them was that you want to be able to say vector A plus vector B and have it do vector addition. You really, 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 really want that if you're doing 3D. The other one was more technical. You want to be able to write an infinite loop. Neither of these things works in JavaScript. An infinite loop locks up the browser, and you can have even a hard time killing the browser. And the other thing was it doesn't handle what's called operator overloading. Python does, many languages do, but JavaScript doesn't. By operator overloading, you mean here's a time sign, asterisk for time sign. If the 2 things are integers, add them as integers. If they're vectors, add them as vectors. And there could be other kinds of objects in principle. So Scherer found some libraries to deal with both of these issues and make it possible for us to do in VPython what we'd always done. Namely, permit infinite loops and do vector additions the way you would want to. So still, what on earth is this? Well, as we'll see later in a little bit more detail, one of the steps that takes place after this has gone through RapidScript, but what I'm showing here is the final product. After doing that, there's some more stuff that's done. And basically, the software that Scherer found parses the JavaScript code, finds the 5 times 3, reports it as this is the left argument, this is the right argument, and this is the operator. Do what you will with it. And what is done is to create this character string, which looks very odd, but if you look at just that much, that looks sort of like a dictionary. You have a thing, in this case a 5, it's a number, so it's in the number class. 5 is an instance of the class number, and that thing is actually in JavaScript essentially what in Python would be called a dictionary. In JavaScript it's called an object literal, but we're getting this particular what's the right term? This is the index, the key. So this is the key into the number class where we're picking up the operation for doing multiplications. And we're passing to the multiplication function this argument, 3. And the net effect is that it picks up a 5 and multiplies it by a 3 and returns it to A. JavaScript lets you change the functionality of even built-in classes like number and string, which is extraordinary. But on the other hand, they also don't give you operator overloading by itself. So that's how that works. And you have a question about this because it's really bizarre. Okay, you're comfortable with that? Okay, so that's what happened to line 2. Line 3, want to make a box, has a position and a color. That syntax is not like what JavaScript code looks like. And RapidScript does some pretty complicated stuff, but look just at this piece for a moment. So here you see position colon vector 100, color dot red. So clearly that's just the equal sign goes into a colon. This is what it looks like to pass stuff to a function in JavaScript. Essentially you're sending a dictionary to the box machinery. Okay? So that's what that is. What's all this other stuff? That's stuff that is there that RapidScript puts in, hence the capital RS, to fix things up in such a way that this will work. It's magic. And we don't need to know the details, but that's where that's coming from. And you will see occasionally rather peculiar looking stuff, and typically it's got a capital RS there. I'll mention that actually what RabbitScript puts there is Greek lowercase rho sigma. And there was a time when I couldn't deal with non-ASCII code, and so I changed their rho sigmas to RSs, but that's what that stuff is. Now, the next thing is line 4. We want to pick up a vector and add a vector to it and put it back. So you will not be surprised that the vector class also has been dinked with so that its plus function operates on this rightmost vector. Okay, so that's where that comes from. Now comes, you defined a function f of x. That comes over here as a function f of x, no big surprise, but there's this odd thing here. The code in the GlowScript library is old JavaScript. It's 2011 vintage JavaScript. Why do I have to even say that? Between 2011 and now, there have been just about every year pretty major upgrades in what JavaScript can and does do. And a fairly recent thing that came to it was async and its partner await, which are in later versions of Python also. And they have to do with pretty arcane stuff about being able to call a function that is going to wait for a while to do something and not return from that function. Stay there until it's done. I'm going to await you finishing that. Before this recent async await capabilities in JavaScript, Cher had to use a library called Streamline that took your program with its infinite loop in it, took the stuff in the infinite loop, put it off in a separate function, arranged to have it called every certain number of milliseconds, and then come back and so on. And the code it generated was vastly more difficult to read than this is. This is not very pretty, but it's at least somewhat readable. So what goes on here is your function might, for all I know, I'm not going to go through here and find it, all the details, it might have something like a pause in it, which means what it ends up meaning is this function has to be prepended with async, because only async functions can contain await calls. And scene.pause is if you go there and you don't want to come back and leave this function until it's actually finished that pause. So these asyncs and awaits get stuck in during part of the compilation process in order to do what needs to be done. And then here you see a call to your own function, and you can see it down here. There's the f, the name of the function, and there's the argument. Sorry, pointed the wrong thing. Here it is. Here's the function, and there's the argument. And this piece here has to do with the print statement. Yeah, I was pointing at the wrong thing. That piece, the print function, has some stuff that goes with it. So that's the kind of thing that happens. There's quite a lot of transformation going from the Python code to the JavaScript code, but it can't be avoided because that's what it has to be. RabbitScript, it ends up that basically the GlowScript stuff is kind of a thin wrapper around JavaScript. It looks like you're writing Python, and you are, but it's really kind of a thin wrapper. In fact, you can insert some JavaScript statements or jQuery statements into your Python code, and RapidScript will pass them right through and it'll still work. So we don't teach our students about all that, but there you are. Questions about this piece? Okay,
sorry.
please.
We're talking about GlowScript VPython. What is GlowScript by itself other than Python? Are there
So originally, yeah, sorry.
things it can be wrapped around?
Originally, at glowscript.org, you had to write your program in JavaScript, and you still can do so. In fact, that first line, if you say GlowScript 2.9, by default it'll be JavaScript, or you can say GlowScript 2.8 JavaScript. And so for the first few years, you had to write your programs in JavaScript. And the growth in the use of GlowScript at glowscript.org went like this, and then when you could write it in Python, it went like that. But you can still write your programs in JavaScript if you prefer. You shouldn't. You shouldn't prefer. Other comment or question? Okay. Now let's look in more detail at the compilation steps, because there's quite a number of them. It's not just RapidScript, but there's a lot of other pieces as well. So, code. We do a fair amount of pre-processing. For example, it always bothered me that a programming language will tell you that you didn't end a string, or you're missing a right parens or something. It gives you no sense of where the error is. And so I actually go through and I track parens, bracket, brace, single quotes, double quotes, triple quotes, and identify what's in there, and keep track in such a way that if you are missing a right paren down here, I can tell you where the bug is. So that's one example of what happens to the pre-processing. There's a lot of other stuff going on. As we're going through this kind of a first pass, we're identifying the names of your functions and where you call those functions. Because later on, after getting through RapidScript, which would barf if we put async and await in there, later on we're going to have to go through in a second pass and prepend async and await in the appropriate places so that your program can, in fact, run at execution time. So there's a bunch of stuff that goes on here. By the way, all of this is basically in one file, GS compiler for GlowScript compiler. We now have got it set up to a state where we can pass it to RapidScript. It comes back to us with JavaScript, but we're still not done. There's a lot of post-processing, which included putting in those asyncs and awaits, a bunch of other kinds of stuff. And then there's the operator overloading stage of saying, okay, but where there's 5 times 3, you got to change that. Now you would say, well, why not just leave it 5 times 3? Yes, but we're not smart enough at execution time to know what the difference between a 5 and an n that happens to be a 5. And so the only safe thing to do is to do this for everything, vectors, numbers, strings, whatever. And it turns out, surprisingly, that the execution speed overhead isn't very big. It's surprisingly small. So that actually works. And now one other thing that happens in here is that we prepend some stuff to all of that code that is, for example, references to other libraries that are going to be used at execution time. So we finally end up with an executable program. And you can see that executable program if you go, when you're editing your code, there's this option share or export code. If you click on that, you'll see that final thing. That's the thing that you can export and put in your own web page. Questions on this structure? Okay. So that's compiling. So More details about the pre-processing step. Remember, that's before going to RapidScript. Check for, talked about the braces, etc. Put those line numbers in. Handle import statements. You may want to say, instead of from VPython import star, you may want to say import VPython, or from VPython import box and sphere and color. So that's in there. I mentioned locating the function calls, and now we pass it on to RapidScript. And coming back, we have to put in some preambles to that code to invoke libraries in particular. Originally, as I said, the program you wrote was in JavaScript, and so the names of the object were things like box, sphere, cone, etc. The Python box are not quite identical. In the original JavaScript implementation at glowscript.org, the box, there was no connection between changing the axis and changing the size. But from time immemorial, namely 2000, a box object, there's a connection. If you change the axis just by making it longer, you also change the size in the axis's direction. The JavaScript definition wasn't like that. The axis and size were decoupled. So to preserve the coupling, there is, in the GlowScript library, there are two box commands. One is named box, and that's the original one, and one is VP underscore box, VPython box, which does have the coupling. And in the post-processing, one of the things that's in the code that you can see, again, if you go and look at, just do the export and look for yourself, is you'll see box equals VP underscore box. And so that statement redefines where a box is going to go when you encounter a box statement. Put in the asyncs and awaits, and there's some other small adjustments that are made. The operator overloading we've covered in the basics. Here are the kinds of things that happen. So we looked at this simple case. That's the standard thing. Numbers, strings. So here, the way you modify an object, such as a string or a number, is by changing its prototype. This is JavaScript jargon. You can, when you tamper with a prototype, you're tampering with the class itself, which is somewhat remarkable. And especially that you can change the prototype of the number class. The vector prototype, for its plus operation, is a function that looks like this. We come in with this function, and what happens is we check to see, is it an instance of a vector, of the vector class. This is JavaScript way of checking type of a class. So if it's not an instance of the vector class, call this function that reports an error. You, student, have tried to add a vector and a scalar. And you can see how valuable that output is. Otherwise, we return a new vector. This has come in as the object of the left argument, essentially. And so we make up a vector, and the new word is used in JavaScript to make a class instance instead of just calling a function. So I believe that now actually has the word class as well as the word function. Is that right? Yeah. So the code base eventually should catch up to modern JavaScript and exploit its capabilities. But at the moment, it's still old JavaScript, which can't be changed because of the commercial internet. And old programs have to keep running. So this has got to be the most stable language ever, despite which they're managing to add things without taking anything away. And they're doing an excellent job of this. Okay, questions here? Okay, so how do we actually set this stuff up? And if you look at the files you have, there's a folder named lib, and there's a subfolder named glow, and in there are the most important files in the whole system. The GS compiler is in a separate folder. I think the folder is called compiling. But just about it, all the really essential files except for that one are in libglow. And primitives.js is, of all those files, the most important file because that's the place where all the definitions of what it means to make a box or a cube or a cone, a box or a cone or a helix or whatever, that's where almost all of it is. There's the implementation of 3D text and extrusions is sufficiently complex that that's actually in its own file, extrude.js. But we're going to be looking at primitives.js later. What you would find in there is there's a function vp_box, which, using a sharer function, invokes a subclass, makes VP_box a subclass of box. What does that mean? It inherits basically all of the functionality of the original JavaScript box, but it adds in some additional things like the coupling between axis and size. Those things. And just for completeness, there's a file that we rarely have to look at, but this file has definitions of the mechanisms that simplify the code that you'll find in primitives.js. What Scherer was concerned about is there so many getters and setters and stuff that became very verbose in just native JavaScript. So he created some functionalities here that made it easier to write and read what's in primitives.js. There are, in the main important objects like box and sphere, there are some special attributes, a special kind of vector. So an example is object.position, where object could be box, sphere, cone. And object.pos is defined to be an attribute vector POS type vector. What's that mean? When you make a change to object.position or any of its XYZ attributes, or the code that does the vector assignments recognizes that this vector has a parent. Its parent is this box object. And when you change the position of this box object, the vector calls the box object's change function to set a flag that this box has been touched. And therefore, the next time you go to render it in 3D, you need to take into account the fact that it has changed. Why do you need to know that's changed? We'll come to back soon, but basically it's that while you're running your program, in your program, object.position is a double precision 64-bit number. But WebGL, being a stripped down version of OpenGL, can only accept 32-bit numbers, single precision floating point numbers. So the last thing that happens before actually rendering a box object is, if necessary, take those 64-bit numbers and make an array of 32-bit numbers, which is what WebGL needs. And that's why we need this changed bit to know whether we have to do that or we don't have to do that. Of course, most of the time we don't have to do that. If you're just changing the camera view, we don't have to redo anything about the details of this box. But that's taken care of by rotation of the camera. But if there's a change, we have to set that. And as I said, for for Python programs, but not JavaScript programs, there's this coupling of axis and length. And finally, there's one other thing that happens with these attribute vectors. When we see that there's a change in a vector that's associated with up or axis, we have to be very careful to keep, if you change the axis, we got to change up as well to keep them being right angles to each other. And so that too is a thing with these special attribute vectors. In your own program, if you say A equals vector 1, 2, 3, and you do things with that, you're not invoking this stuff. You're not making special attribute vectors, you're just making vectors. Ordinary vectors don't go around saying, oh, but you also have to change this box, because no, it's just a vector. It's just a vector. About 60 times a second, we call upon WebGL to paint a new picture of the objects that exist, of the currently visible objects, and using their current attributes and folding in the effects of the current camera position, which your program might have set or the user might have set. And here we have this conversion from 64-bit to 32-bit. And the package that gets sent to WebGL is just 5 4 vectors. What's a 4 vector? Well, no, the fourth dimension here is not time. The first 3 are x, y, and z for the 5 key attribute vectors for an object: position, size, axis, up, and color. Those 5, they're all 3 vectors. Now, as a physicist, you can object that it's okay to say position and axis are vectors, but how can size be a vector? How can color be a vector? Sorry, that's just how it is. So color is sort of understandable because it's got 3 components, either RGB or hue, saturation, value. But in CS jargon, these things, all of those things, if it's got 3 things and it does stuff, it's a vector. So yes, you may want to tell your students these size isn't really a vector, but it does have 3 numbers. And so if you're doing 3D, it's kind of unavoidable that how long it is and how high it is and how thick it is and so on, those are actually 3 numbers that you might as well package up as a vector. So those are in there, but there's a bunch of other stuff as well, some scalars. The texture that you've applied, if any. Now, that sounds like a lot of stuff. Well, yes, it is. It's a pointer. It's a number pointing at a texture. And opacity, that's 1 floating point number. Shininess is a 1 floating point number. Emissive is true or false. That stuff is packed into these 4th components of these 4 vectors. So you end up with 80 total bytes for the instance of a box or a sphere object, which is pretty compact. So there's so that's how the packaging of the data for a particular object goes. Now, in the code, it's important to know this convention, which was due to Scherer. Very often you will see that some attribute has 2 forms. For example, a box could have an opacity, but you'll find in the code references to __ opacity. And what's going on there is that when you go and set opacity to 0.5, we kind of need to know about that. It means we may have to repackage the stuff for rendering, for example. So we want to know. And so what happens is that there are getters and setters such that when you change object.opacity What we do is we change internally object.__ opacity. And when you ask for it, when you read up object opacity, we read up object.__ opacity. In a deep sense, there is no object.opacity in the code anywhere. There are only these __ versions, so that we know when you're asking for something and we know when you've changed it. So you'll see that a lot. And occasionally, there are times when in our own code, we know that it's not necessary to invoke any of that stuff. We can safely make this change. Or, for example, when we're trying to make sure that the up and the axis are staying at right angles to each other, we actually want to be working with the __ version so as not to invoke the machinery that's going to try to do this while we're trying to do this, because then, okay, you can see the problems. So you'll see this throughout the GlowScript code. You see a ton of __ versions. And I'll mention that it happens in the VPython 7 world, with installed Python. They happen to be single underscores because that's how John Cody started out with it. But it's kind of the same idea. We're control freaks. We want to know when you do anything to our objects that we've made for you. Animations. How does that work? Well, as you know, the rate statement clamps things that do no more than 200 iterations of this while loop that contains the rate statement. But it has another responsibility. It's also watching the clock, basically, is one way to say it, that it ensures that as much as possible, it will try to call upon the renderer 60 times a second. To put it more clearly, it sets timers on itself that allows the renderer to run. The renderer itself, the renderer goes through and tells WebGL do all this stuff, and the last thing it does is it says, run me again a 60th of a second from now. And that's kind of typical JavaScript programming and web programming. You say, I do this task, and then I tell the JavaScript environment, I want you to call me again this many milliseconds ahead. In this case, about 17 milliseconds from now. So the rate statement in the installed Python world, it really has to watch the clock. In the JavaScript world, the rate statement just has to make sure that it's open to, that it's not going to proceed to the next statement, and that it's going to allow the renderer to run 60 times a second if it can. The details of this are a little tricky. 200, you've got 60 time slots, and you're going to do 200, you want to do 2 of them in a second, and 260 don't really fit together. And so what it really does, it says, in this next opportunity for rendering, 60 divided, it goes into 23 and something. So do 3 renders, bang, 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 without waiting, and then sleep for the rest of the 17 milliseconds. Is basically what's happened. So the rates are spaced over times in a kind of an odd way. But so the timing, put it this way, the timing isn't perfect. You say I want 200 iterations, or you probably won't get exactly 200. Sorry. So that's basically what's happening with the rate statement, and it's actually located in this very important file which contains all of the interface to WebGL, which is, I repeat, is a very low-level library, and so it's unpleasant, difficult code, but it's there, and I'm glad Cher did that part. Now, something about the rendering. So about 60 times a second. We need to send object data to WebGL. That means, if necessary, redoing that 64 to 32-bit conversion thing. But the GPU, the graphics processing unit, has in its memory things like what a canonical box looks like. And we'll say a little bit more about that, what a canonical sphere looks like. It has data about what objects look like in their most primitive, basic default form. But we need to tell it every render time. This is not a GPU memory. Perhaps it could be, but it will require some complex management of the memory to do that. But at the moment, I repeat, the graphics processing unit knows about boxes and spheres, but it doesn't know about this particular box or sphere unless you tell it every get to render. So we send that data over. On the graphics processing unit, there's two kinds of processors. Things that for historical reasons partly are called vertex shaders and fragment shaders. What a vertex shader is this. Here's the platonic box, the ideal box. Here's your box, which is long and thin and is pointing off in that direction. And that's the specific data. And that data is used by the vertex shaders to figure out where the corners will show up on a 2D display. So here's this box, and depending where the camera is, let's say the camera is there, the vertex shaders have to figure out where is this point, where is this point, where is this point, when projected onto a 2D screen that you observe. So vertex is the right word. Because what is a box? Well, it's a set of triangles. Vertex, vertex, vertex is one triangle. Vertex, vertex, vertex is another triangle. And so this can be done in parallel, though, because one of the, so on the graphics card, there's a ton of processors. A typical number would be like, what, 1,000 maybe, Ruth? Something like? 2,000? 2,000 of these. So your processor number 1, Craig is processor number 2, Steve is processor number 3. You are going to work on figuring out where that corner shows up on the screen. You're going to figure out where this one is going to be, and you're going to figure out where that one is. Now we have the positions of the corners of that triangle as they'll be on the 2D screen. There is invoked on the card, hidden from you. You don't have any control over this at all, as far as I know. A rasterizer, which now that it has these 3 corners, can fill in that entire triangle with all the pixels that are on your particular device. It figures out where all of those are. And there's a lot of them. And that too is farmed out to more than one fragment shader when it gets to it. But you have this rasterization process so that you know what pixels are inside this triangle. And the coin of the realm is triangles. It's triangles everywhere. That's all the graphics card can deal with, basically, is triangles in some fundamental sense. When this has been done, now that we know all of these vertexes and all of the triangles within, so we know all the triangles and we know all of the points within those triangles, fragment shaders can work on, that fragment shader is going to work on this pixel, and you're going to work on the next one, you're going to work on the next one, you're going to work on the next one. You have a whole bunch of processors all looking at individual pixels and deciding what color they should be. Well, what color should they be? Well, first of all, there's the color of the object. Secondly, maybe there's a texture on it. Third, maybe there's special lighting of a different color or different position. All of that stuff affects the color, and the fragment shader has code to figure that out and determine a color. Now, There's a problem, though, of having you guys working the pixels for the front of this box, and you people working on the triangles on the back of the box, which you're not even going to want to see ultimately. So how do we get rid of the hidden line problem? How does that work? Lovely piece of specialized hardware. What the fragment shader does, so you decide that this pixel should be green. She's working on a triangle that is either in front of or behind that. She thinks that same pixel, physical pixel on the screen, she thinks it should be cyan. Now, some people will argue between whether this looks like green or cyan to them, but let's make it red. So you're trying to make it green, you're trying to make it red. And let's say your triangle is in front of hers, so it should end up being green instead of red. But you're working independently, in parallel. Who breaks the tie? It's very clever. When the fragment shader, in the fragment shader, say this pixel should be green, and its Z depth from the camera is 5 centimeters. She determines, no, that pixel should be red, and it's 7 centimeters from the camera. When you wrote the 5, the red and the 5 here, the color for the pixel went in there, and for that pixel, corresponding to that pixel location, you actually set the number to 5. And when she tries to store there, the store operation itself, as an atomic operation that can't be interrupted, when she goes to store a red for a thing that's 7 centimeters, 2 centimeters behind yours, the machinery ignores your attempt to store, throws it away. Isn't that cool? And that's how the parallelism can work on a GPU. That is absolutely critical. This is critical and hardly ever talked about. It took us a long time, Ruth and me, to find out how is this working, because that's all hidden. It was easier to find information that explained how this collision was resolved.
So how does opacity work in that case?
How does
opacity?
So opacity is incredibly difficult to handle transparency in WebGL and OpenGL. And in fact, as far as I know, I was the first person to handle it for WebGL. What you have, there are various schemes. You can read about it. I think I have a reference to it later in the talk. But the scheme that I use, which Scherer told me about, I wouldn't have known about it on my own, is called depth peeling. Suppose I have a box, a cube surrounded by a sphere. So a box object, an opaque box object surrounded by a larger transparent sphere. How is this going to work out? I'm glad you asked. So the first thing is we go through and render only the opaque objects. We have to identify them, and there should be a more efficient scheme than is currently implemented there. But right now, we figure out which things are opaque, and so in the first pass, we go and find where the opaque things are, and in particular, given where the camera is and where the the opaque object is, we record in a pixel map how deep the frontmost piece of those opaque objects is. Because mind you, once we actually render them to an off-screen pixel map, so we've got in there, we have the depths of the fronts of all the opaque objects. Okay, so we know where that is. Now, in the next pass, we start working on transparent things. And here we just got one level of transparencies, but if we had several, I'll comment on that. So what we do now is we try rendering transparent objects. Again, looking to find the frontmost part of it. What we're going to identify is this whole front hemisphere, is in front of, well, in fact, sorry, yes, the front, it's going to be the front hemisphere that's going to show up. And so we record all that, and then we remove that front hemisphere basically, and we go again, and this time we're going to pick up the back part of it. But the thing that's the part of the sphere that's behind the box, we're going to end up finding later on that it's at a deeper depth than the opaque thing. So that one's not going to show up at all. But the stuff to the sides will. But here you're looking through just one piece of transparent stuff. Over here you're looking through two. So you've got these depth peels. In this case they're basically going to be three peels. The opaque, the front of the sphere, and the back of the sphere. Now you go through and the fragment shaders are going to pick up how many go through and weight accordingly the opacity and the color, and you end up with a final color. Now this is hand waving, but there is more information as you'll see later. Not detailed here, but there's a link in the help on how that works. So depth peeling, and it's somewhat ironic. If you look at the coin of the realm at this level, mostly it's all 4 vectors, and you would think that the 4th vector would most naturally be opacity, but it isn't. It's something else, and so handling transparency is not built in to WebGL. It requires a lot of effort. Okay, and this code is written in a special language, graphics library shader language. It looks sort of like C++, but it does have vector operations in it. It handles 3 and 4 vectors. They're called vectors. So this code is very different from the other code. JavaScript, but this is not. And there is that one page of Python code that's the server code. Any questions on the rendering? Rendering under Caesar, or okay, or seizures, or okay. More about GPU. The graphics program, the graphics card has its own memory, and those memories are getting bigger and bigger and bigger. 64 megabytes is not, I think, terribly unusual by now, maybe. Stored in, when you create a canvas, and recall that in a VPython program you can have multiple canvases. For every canvas there's an instance of the renderer, because they're all independent. When you create a canvas, you also set up a bunch of what are called meshes in mesh.js. So I'll take a model of the box object. You'll find in mesh.js a description of a 1 by 1 by 1 box in terms of 8 vertices, 12 triangles. There's 6 faces, so 2 triangles to face. And for each vertex, there's a 3D position with the 0, 0, 0 being at the center of it. There's a normal, there's a color, and texture coordinates for how to, if you got a texture to put on this thing, where in this triangle does this piece of the texture go. And then for any particular box, an instance of the box class, this model information plus the particulars of this particular box is what goes together to get the 3D box that you see. And we have in the memory, there's models of a box, a sphere, a cylinder, a cone, a pyramid. Compound objects have the same status of primitives. That is, when you, in VPython, you can compound a box together with a cone or an arrow or whatever. And their meshes got meshed. We find all of the triangles, all of the characteristics of those objects, and make up put in GPU memory the vertex and triangle information about that compound, and now you're treating it just like any other compound. You can move the thing. It's very efficient because it's a model that's in GPU memory. The curve is cylinders with a hemisphere cap, and if you look very closely, it's still the case that the very first piece is open. It really should have a hemispherical cap on it, but never mind. Nobody has complained, and so nothing's been done about it. You can, of course, build arbitrary objects from triangles, but they will not be out there in GPU memory. They're going to be triangles. Extrusions actually do end up as compounds, basically, and as does 3D text. Questions here? So some additional technical details. Some of these have already been treated. I explained how the Z-depth blocking is done by the GPU hardware so that you don't see the back of stuff. Transparency is a depth peeling algorithm, which I sketched. Mouse picking is amusing. It's a standard, like depth peeling, it's a standard scheme. When you make a box and another box and another box, they actually contain an ID number, 1, 2, 3. And we keep those numbers around. And when you say, tell me where the mouse is, scene.mouse.pick, what's that value? We render, silently off screen, we render the scene using as colors those ID numbers. So you're going to get a color that's 1 and for this object, and 2 for that, and 3 for that. So they actually all have different colors, your boxes. And one of those boxes is in front of the other box. So we render, and then we look at the color of the pixel where the mouse currently is and see what color it is. And it back as 2. It says, oh, okay, I don't know how many boxes are lined up in a row that I can't see them, but the frontmost box, there is a box here, the frontmost box, and it's number 2 box. And so we send back to you the equivalent of it's number 2 box. Now you called it Zork, and what we return to you is Zork. It's a handle on the box. So that's how the mouse picking works. And interestingly, for mouse picking, we have to turn off what's called auto-aliasing. So auto-aliasing is or aliasing even, it's a thing that's built into renderers that if you're drawing a line that's not quite horizontal, it really in pixels it's going to have little steps in it, right? And it's not going to look very good. And it's going to look jagged. So aliasing processes, which are done by GPUs, pardon? Anti-aliasing, thank you. Anti-aliasing. The GPU itself can fill in some of those steps with a little bit of a grayer version of the neighboring color and so on, in such a way as to fool the eye into that it looks a lot better. Alas, when we're dealing with multiple renders in the case of handling opacity, it can't be anti-aliased. And so if you have one transparent object in your 1,000 objects on the screen, alas, anti-aliasing is turned off for the entire scene. Sorry, there's not a way around that at the moment. But in mouse picking, we deliberately turn off anti-aliasing. Why? Because if you've got 2 boxes kind of near each other and you're trying to pick one of the 2, well, anti-aliasing dinks with those sharp edges to make them not quite sharp so that they're not looking jagged, and you could end up getting a color that's intermediate between 1 and 2, or it's not not something any of your objects has as ID. So that's sort of amusing. At this location, and that's on your notes, is some of the details about that. Okay. A canvas. So this is perhaps the second most important file in the libglow folder. It's got the machinery for making a canvas and methods having to do with mouse and keyboard handling. It sets up some default lighting that, which you of course can change, but it's a key place. And a lot of the event handling is done at a lower level in other files, but ultimately when it's about to get to the user, it's methods here. And there are two kinds of canvases. There's the 3D canvas you create. We put a transparent 2D canvas in front of that where label objects go. So that's those text objects in front of the scene. It happens that WebGL, like OpenGL, just doesn't do anything with text. 0, 0, 0. Nothing. As though you would never want to do text in a 3D scene. So, as you know, we have two ways of dealing with text. One is a label. That's 2D text that goes into a 2D canvas in front of the 3D canvas. And 2D canvases do know about things like displaying text and even drawing lines and boxes and what have you. So anytime you have a label object, it's appearing there. Now we'll move the stuff around depending if you change the camera view and so on, but that's where it goes. 3D canvases are special. In the autoscale file, autoscale.js, is the machinery for figuring out where to put the camera. As you add more and more stuff to a scene, or the object moves far away, the camera has to move back in order to make all the scene visible, and that's where that's done. It's currently done in the CPU. I did try, but unsuccessfully, but maybe one of you will do this, to do it in the GPU. It'd be more appropriate for the GPU to figure out where to put the camera, rather than, because it could do all this parallelization of the calculation. But currently it's all done on the CPU, and it's somewhat expensive. The low-level mouse handling is in orbitalcamera.js. A graph is a 2D canvas. And by the way, Aaron just recently has made some very interesting stuff not released yet that opens up another capability that Plotly has as a graphing package. So there'll be more to see. Some web issues. There's a directory IDE, Integrated Development Environment, API.py. It's a Python program. It's 2.7, Python 2.7. This is a Google App Engine application, which Scherer appropriately chose as the environment, and it turns out to have been a good choice. And up until now, the server part of a Google App Engine application had to be written. If you were using Python, there were other things you could use, Java, whatever. But if you're using Python, it had to be Python 2.7. That's changing. It is now possible for it to be Python 3, and we are being urged to make that transition. It's a leisurely one because although Python.org support for Python 2.7 ended on January 1st, 2020, so a couple weeks ago, Google has made a kind of a commitment to have Google App Engine and other things continue to run using Python 2.7 because they have so much code of their own of that kind that they haven't converted. Nevertheless, they're encouraging us and enabling us to move to Python 3 ourselves now. So I do think that it should be for cleanliness and no other reason. Also in that IDE folder, so the server code has to give the browser stuff like fonts and textures, things like that. It has to get stuff from the data store and put your stuff in the data store. That's what it's doing. It's one relatively short file. So in a way, there's not a big effort required, presumably, to go from 2 to 3. The big concern is that the data store has to still work. I think many of you who have programs at glowscript.org would prefer that the program still be there after that change. Is there a show of hands on this? Okay. The editor that's there is the ACE editor. It's not ideal. It probably should be replaced with something better, more modern. ACE does not work on mobile devices, so if you're on a tablet or a phone, what you get is a little editor that I wrote, editor.js. When you run at glowscript.org, you're actually running in a sandbox that you don't have access to stuff you shouldn't have access to. And so that's the corresponding code that you'll see is the folder named untrusted. So we don't trust any of you to run programs on our website. The JavaScript that's used, I pointed out that it's 2011 vintage JavaScript, except for the recent introduction of await and async. Semicolons, you may recall in the first thing I showed you, there were semicolons at the ends of lines. And that is classic JavaScript, and it's what many programmers think you should always do. Because if you work really hard at it, you can find a particular obscure case that probably never comes up, where if you don't use a semicolon, it doesn't do what you wanted. So Cher made the decision, and I agree completely, that we are basically a semicolon-free zone. We just don't have them there because it just makes it harder to read. There's one more thing to read. We can't avoid using lots of braces. Ruth once commented very appropriately concerning many programming languages, not Python. Every brace is an opportunity for an error. We do have braces in the JavaScript code. Some of the libraries that we use, I had to dink with, because this whole project starting in 2011, things like the require function that's quite widely used now in JavaScript environments, it didn't even exist, or the notion of it or anything. So we kind of have code that's not comfortable with some of kind of existing and going forward libraries. That also is not great, and at some point that probably should be dealt with. But when we use a library like RapidScript, we don't get it from the RapidScript URL. We get a copy, and every now and then we may or may not update it if we feel a need. So basically, the libraries, third-party libraries that we depend on, we have our own copies, and that's true of jQuery as well, for example. A lot of the web manipulation uses jQuery commands. Speed issues, I may not have mentioned or may have. GlowScript program, a VPython program that's heavily computational runs 4 or 5 times faster at glowscript.org than it does with installed Python. On the other hand, of course, with the Python program, you could beef it up with NumPy or Numbar or whatever, but just native code. I believe a key factor is that Python loops have large overhead, and JavaScript loops seem to have none. I don't know why. I don't know why in either case, actually. But the penalty, of course, is that because the GlowScript environment is a very thin wrapper around JavaScript, you do not have access to Python to Python modules like NumPy or other. one of the things that seems plausible is that it ought to be possible to do something like the following. Suppose you've written a program at glowscript.org, and you have your own program that you'd like to use essentially as a module, as a library. You've got 5 programs that use your own code that's also written in GlowScript and VPython. Let's call that thing lib. So here's your file lib. It's Spickelmeyer blah 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 lib. It ought to be possible in any of these 5 programs of yours, Steve, to say include blah 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 lib, which would just bring in that Python code and compile it. That would be useful, I think. That still doesn't get you Python modules, but it gets your own module that you wrote in Python. You can already import libraries written in JavaScript, and I've done that myself on occasion. Some of you have seen our program that shows the surface charge distributions on circuits. That thing calls JavaScript libraries. What is in those libraries? It's just the distributions, which were calculated offline using Python. But that's an example. As I mentioned, there's this need to go from 2 to 3. The Google's own documentation on making the transition says there's nothing, as far as I could see, about how you preserve the data store. There's some statement that it will be preserved, but you actually have to reference it in a different way. But I did find, and then I forgot about it, and Scherer found it again, this link, and I've actually sent this to Google to say you should include some of this information because it's actually crucial. For more information, the one single thing there is at brucesherwood.net, there's a blog article on a detailed timeline for the development. It gives a lot more details than I gave here. The next is the GitHub repository for the source code, which you actually went to download probably the zip file or clone it or something. And then here's the local.html. That's where you went to find out how to get the code to run locally. VPython.org, obtaining and using the various flavors of VPython. There are now many of them, but they all depend on the GlowScript library. And that's why we're talking about the GlowScript library here. That's why we're going to work with it in the rest of the afternoon. It's used in a lot of different places. That's the common element. And it's a non-negligible amount of code. Trinket.io, Aaron Titus is going to run a workshop tomorrow morning on using Trinket.io, which is quite a lovely and interesting environment, especially for educators. And one of its options there is to use essentially the GlowScript version of VPython, which they've embedded in what can be documents that describe what you could do, and right there in the middle of the page saying you should do this, here's an editor and an execution of the thing you should do, hopefully if you've done it right. GlowScript. Matterinteractions.org is the curriculum that Ruth and I and Aaron has joined us in this effort. It's calculus-based intro physics in which VPython plays a key role because we saw it was absolutely essential to include computation in the intro physics course because it's central to all of STEM, but way underrepresented, especially in intro courses. But the problem is most of our STEM freshmen have never written a program before. They've never installed anything. They don't know about folders and files. So the programming environment has to be extremely easy to learn and use. That benefits us too, because we've written lots of demo programs to use in class, and our efficiency has sped up. At one point, with a colleague, a colleague and I went through a MOOC on 3JS, which is one of the more popular 3D environments, libraries for JavaScript, and to make a static image of the dunking bird device that does this. And so I wrote this program, and then I thought, well, let me just rewrite it in VPython and just see. It was a factor of 5 in length, the number of lines of code. Factor of 5. That converts into time. And as you may know, there's a famous cartoon on the subject. Einstein is at the blackboard. It's covered with formulas, and the caption says, I think it was Sidney Harris who did the cartoon, all these cartoons, all these arcane equations, and the caption is, Einstein discovers that time is actually money. And our 70 demo programs that Ruth and I have written to vivify various intro physics concepts.